What building was it in again?
ECA 225. So I will post an announcement on Blackboard that'll have all the details of everything between now and when you're done with the final exam. But yeah, in the meantime, ECA 225, noon to 3 Monday. Study session, office hours. Look over your old tests. Work on the practice problems. So the more you can do, the more you work on those exam practice problems and the web work before you get there, that's going to be, the better that will be for you, right? So don't start your studying at this thing. Because you want to have the chance to, have thought about it and ask questions and bounce ideas off each other, get things straightened out with me. So don't start your studying noon on Monday at the study session. Work hard over the weekend and then get your questions answered here at this, okay? Like I said, come and go as you please. You don't have to come at noon and leave at 3. Questions about that? Then the final exam is Tuesday night. Again, all details will be on Blackboard. Tuesday night, 7 p.m. I think it's in the SCOB building. But again, that's, where's that? SCOB is like, it's on Orange Street. It's kind of close to the bookstore. Really close to the bookstore, okay? Okay, questions about that kind of stuff? All right, and then there might be another web work due like Monday or something, like the last one. I don't remember or not. There's one due tonight at 7, right?
No.
No? Oh, then why didn't you let me know? So there's always this one button I have to click at the very end after doing all the work to set it up. And if I don't click that last button, you won't see it. So if you should see it and you don't, then email me. Okay, it happens. So I'll try to square that away this afternoon. But just watch Blackboard, watch web work for there may be an additional assignment that I post today or something like that. Any questions? Okay, study. You got to study. Lots of different times sitting down to study, asking lots of questions, and especially before this. And then we'll see you on Monday at noon to 3. Okay, so let's we're going to do a summary and a recap of vector calculus. It's been an awesome journey here. Let's tie it all together. So really, this vector calculus is very much centered around this gradient operator. This gradient operator, what's that? That's like this vector of telling you to differentiate with respect to x, y, and z. Right? It's not really a vector. It's a vector of operations, of derivatives. So it's this, right? Take the partial with respect to x. Take the partial with respect to y. Or apply. Apply the partial with respect to x with respect to y with respect to z. So this is this gradient operator. We saw this. And so given a multivariable function and or a vector field, the first thing we saw was what? The gradient of f, a multivariable function, right? Remember what that was. What did that give? What did the gradient of a multivariable function give? Right, so is a vector function. So when you take the gradient of a multivariable function, you get this vector function that shows you direction of greatest rate of change and also magnitude of greatest rate of change, right? The magnitude of that vector is the rate of change, and the direction of the vector is the direction of max rate of change for the function f. That was the gradient of f, right, of a multivariable function. Mostly we saw it with the two variable functions. So that was what we call the gradients, right? The gradients. And then we saw the gradient cross f as a vector field, right? Which gave us a new vector field, right? Gradient cross f was a new vector field taken from f, and what was that? That was the curl, right? That was the curl. So these are all derivatives, right? The gradient operator is essentially derivative, right? So gradient of f is like the derivative of a multivariable function. And what do you get when you get that? You get a vector function. The curl of f is essentially a derivative of f. F being a vector field, and the curl is another vector field. So you get another vector field when you take the curl of f. And what was the last one? The gradient, what? Dot f, right? And here, the gradient dot f was, f is a vector field, and then what's the gradient dot f? What kind of thing is that? That takes you back to a scalar function, a multivariable function, right? That's a multivariable function of x, y, and z. And that, what was that? That's the divergence, right? So again, the gradient operator is essentially the derivative, right? It's these partial derivatives. So, but it's applied differently in different situations, right? So, apply it to a multivariable function, you get a gradient field. Apply it to a vector function, two different ways. You get a curl, which is rotational rate of change, or you get divergence, which is expansion and contraction rate of change, which is a scalar or multivariable function. Okay, but it gets even better, because each one of these has an associated fundamental theorem with it, right? Each one of these has an associated fundamental theorem with it. What about the gradient of f? Which fundamental theorem was that? Do you remember? Not Green's. Line integrals. Okay? It says that if you accumulate little bits of this gradient field along a path, right? Along a path, dr. The most common application of this was work. So if you accumulate at this rate along this path, c, bit by bit, it's the same as what the net change in the original function, right? So it's the net change in our quantity function f. So accumulating at the rate, this rate of change, is the same as the overall change, the net change, final minus initial. Okay, what about the curl? So we saw there was a fundamental theorem associated with the curl. Which one was that? Stokes' theorem. It's the same thing. Well, it's very similar. Again, we're going to accumulate across the surface at this rate, right? This rotational rate. Dot ds, which we called the flux of the curl. And what's that? Well, that's the same as the net change around the boundary. The net change around the boundary, or the line integral around the boundary of the surface. And then finally, the divergence. Which fundamental theorem was that? Divergence theorem, the divergence theorem, right? And again, what are we doing? We're using the rate of change to calculate flux, one little element at a time throughout a solid, right? We're using the rate of change to calculate the flux, one little element at a time throughout the solid. And when you do that, that's the same as the net flux out of the boundary, right? The net flux out of the boundary, which is the S, the outer surface. It's always using the rate of change to accumulate bits of the quantity. That will be equal to the overall change in the quantity. And that's associated with like the boundary, right? It's the same. It's this rate. Okay. What about if our vector field for the what about for the curl? What about the vector field is entirely in the xy plane? So then what do we end up with? The curl is just totally in the z direction. So the x and y directions are 0, so 0, 0, and then what's this? Qx, partial of q with respect to x, minus partial of p with respect to y. Right? Over the region. So somebody over here has been waiting to say this all class. What is this? What's this? So curl, when you do Stokes' theorem in the xy plane, you just have a vector field in the xy plane. Your curl just amounts to 0, 0, and then that z component. And then Stokes' theorem becomes Green's theorem, right? So Green's theorem is just a special case of Stokes' theorem, where your field is in the xy plane, and your curl is in the z direction totally. So when we did Green's theorem, we were just doing a special case of Stokes' theorem. And then we also saw last class, for that web work problem, we saw the special case of divergence theorem in the xy plane. Remember that? It's important, right? So the Stokes' theorem has its R2 version, it's Green's theorem. Divergence theorem has its R2 version. Doesn't have a name, but that problem in the web work was a really good example of it. Okay, any questions so far? Okay, so then you could ask questions like, does it make sense to do the divergence of f, the curl of the gradient field? So knowing that the divergence needs what? Evaluating the divergence, what do you evaluate it of? Multivariable function or vector field? So is this defined or not? Not defined, right? What about this? Can you take the curl of the gradient of a multivariable function? Would that make sense? Is that defined or not defined? That's defined because this is a vector field. You take the curl of a vector field. That's defined. What about the gradient of the divergence of f? Is this defined or not? Is that defined or not? How about just the divergence of f of vector field? Is that okay? And what do you get? Scalar function. So can we take the gradient of a scalar function? Yeah. Yeah. This is a scalar function. This is the gradient of a scalar function. So this is a scalar function. When you take the gradient of it, it returns you back a different vector function. This is defined. Perfectly good. Those who said no, does that make sense? Is that better? So we can write all kinds of examples of this. And so know that curl operates on a vector function. The gradient operates on just the gradient of, you can do the gradient of a multivariable function. Divergence operates on a vector function. How about this? Defined or not? No, why not? Right, right. So how could we change this to make it right? So do what? So this is no. But what would be right? Div curl. That would work. See that? This doesn't work. This does. And remember, if the curl is 0, if you have a vector field and its curl is 0, what do we call that? Irrotational, and that means it's an conservative vector field. What about if divergence is 0? Remember, did we put a name for that? We should have. Incompressible. Incompressible, right? There's no tendency of contraction or expansion anywhere, point-wise, anywhere in the field. Incompressible is if the divergence is 0. But that's unrelated to being conservative or not. Yes, sir?
Does Green's theorem work only in the xy plane or any plane of R?
Yeah, so we could flip it and we could do it in the YZ plane. But it's just if you are in a single plane, then you're usually just use the XY plane. So yeah, so you could do a YZ plane version of the Stokes theorem. But just normally, if we're in R2, we use X and Y. Other questions? Okay, so pretty cool how this all comes together. Make sure you know how these are all, analogous to one another. These are all fundamental theorems. They all have those very important key elements, and they all have them. So I've talked through it many times. You make sure you can talk through it and explain it to someone else. What's the same about all those? And there's like 5 different things or 4 different things. Okay, so let's do. I have a last example that brings a lot of this together. Application, pretty cool. So I have this. So I have this. This is a bathtub drain, and this is a flow field. It's like a velocity field of water, okay, flowing down the drain. So imagine if you have just an open circle and you put one of those like mesh catch things, right? And they're like the shape of a hemisphere. So that's what that gray thing is. Imagine that, okay? So that field is it's bigger. All right. So this is the field. I'm trying to show it all at the same time. Maybe if I do this. Perfect. There we go. Okay. All right. So here's this flow field F. It's just written vertically instead of horizontally. But this is the P, Q, and R for F, which you see here in turquoise. It's our water velocity function. So I want to find the flow rate of the water through not the hemisphere drain, but this disk that would be like the continuation of the bottom of the bathtub, right? So we want to find the flow rate through there. So that can just be air. There doesn't need to be anything there for us to calculate what the flow rate through there is, okay? And then your next task is going to be to find the flow rate of the water through the strainer, the hemisphere, okay? And then I'm going to introduce, after we do numbers 1 and 2, I'm going to introduce another function g, and we'll do questions 3 and 4. So this is function f down here. And it's the velocity flow field of the water going down the drain. So I'll say 1 is pretty Pretty easy. We have to make sure we know what we're doing. Okay, easier, I'll say. So this is harder, but or is there something ingenious we can do? That's a hint. So I'll take attendance and give you a couple minutes and see how we. So we got this big toolbox now of stuff. Flux integrals, Stokes theorem, divergence theorem, this is fundamental theorem of line integrals. Everything we know about, all this vector calculus. So it's kind of like you have to figure out what applies, right? What applies to answer these questions. What? He says no. You want the flux of F. So Stokes' theorem is for what? Doing the flux of the curl of F, right? Very specific thing. Is that what we're doing? So then you'd have an option, right? If it were Stokes' theorem, you'd have an option then to do what instead? The circulation integral around the boundary of your surface. Does that apply to question number 1? You still going with no? It's okay to be wrong. What do you think?
I think it does.
You think it does apply?
Yeah.
You think so you think this is asking for the flux of the curl?
That's the flux through the surface. You can't do that.
But the key thing here is that the function that you're doing the flux of in Stokes' theorem would be the curl of some function. Is that what we're doing? Yeah.
No, aren't we just doing just the flux right through the surface? So we're not using Stokes theorem?
Okay, so, well, Stokes' theorem it's not about the surface, right? Our choice here to do Stokes' theorem or not, they both, Flux and Stokes' theorem are both flux through a surface. The question is, what is it we're taking the flux of? Is it F or the curl of F? Right? So our general formula for flux is just this. Those are both surface integrals through the surface. The question is, do we want the flux of F or the curl of F? If we want the flow rate of the water through the drain. Just F. Just F. So, does Stokes apply? Does not apply. It's not talking about the curl of F, it's talking about F. All right, so we're going to do the flux of F through the unit disk. The unit disk is just this open region, circular region, right? Disk. So, did you get that? Anyone got that? What do we have to do that? Do we need to parameterize the surface? Actually, we don't in this case. Why not? We use the normal vector, right? This is the xy plane. So we can use that nice shortcut where we do f dot n ds. Remember that? We can do this one. And what is n? So yeah, so you can orient it however you want. It does because you're setting this up. So you can orient it up or down, but then your result should be consistent with how is water flowing. If we orient it up, what do we expect for an answer? We expect a negative, right? Because water's clearly going through that downward. So let's do that. We'll orient it upward. And then what's our f? So it doesn't matter. Noticing 0, 0, it doesn't matter. I'll just write P and Q. Those are going to go to 0, right? So all we care about is R. So what is that in the xy plane? -1. We can set, because we're in the xy plane, z is 0, so our r is -1. Okay, and then that's dA. So we got 0, 0, not 0, 0, sorry, PQ -1. I'm just abbreviating this for P, this is Q, because we don't need them. They're going to go away, 0, 0, 1. And then dA, and that's over the disk, the unit disk. And if you do the math, so dA, is it just, we're going to use r and theta, right? Is it going to be dr d theta or r dr d theta? We're going to need the r. We're going to need the r here. Because dA is r dr d theta. So that's going to give you, what's the answer? Anyone got it? This is r dr d theta. So r goes from 0 to 1, theta, 0 to 2 pi, negative pi. Is that what we expected? Negative? Yeah, because we oriented upward, water's flowing down. So our flux, or our flow rate, is negative pi. All right, now we want to do the same thing, flow rate of the water through the strainer, the hemisphere. What would that look like? So first of all, is that using Stokes or not? Does Stokes apply to this one? No, it's the same question, just a different surface, right? It's still just asking for the flux of F, right? The flow rate of F, but now a different surface. How are we going to do this? Okay, so let's put that on hold. If we were to do this directly, what would it look like to do this directly? What would we have to do? Parameterize the sphere. And what parameters might we use for that? What are our U and V? Yep. Did you have a Weber problem like that? Did you have to do one of? Yeah. It wasn't pretty, but you had to do it once. Everyone's got to do it once. Okay. So, yeah. So we're going to parameterize that surface. If you're parameterizing a sphere, phi and theta. Yes, I hate it too. It's ugly. It's bad. So we think we've got all these other, he's got these tools. Is there something we can apply to make our life easier here? Yeah. How? So how would you apply it? So that's what Jonas said too? Okay. But isn't that divergence theorem for a solid with a closed surface around it? Is that hemisphere a closed surface?
You just subtract what we got from before.
Right. So we can, exactly. So we can do that divergence theorem, and that triple integral of the divergence of F over that solid will be the same as what? The sum of the two, the hemisphere and the top disk. We already know what the top disk is. So we can back calculate the, this is a better plan than this, right? Much better plan than this. But everyone's got to do it once. Okay, so let's do that. Here we go. So we're going to do, so what about the divergence of this? Find the divergence. Here we go. Not as bad as it looks. Partial of this with respect to x. Not bad, actually. What is it? Negative z over z squared plus 1 squared. Not bad. Okay. Partial of this one with respect to y is? Same thing. See it? All right. Partial of the last one with respect to z. So we think of this as z squared plus 1 to the negative 1. So what we'll have, z squared plus 1 to the negative 2. Times what? So then there'd be a negative 1, this negative 1, and then the negative 1 from the exponent, and then what else? a 2z.
The exponent on the bottom should just be positive.
Thank you.
Down there.
Yeah. What is it? Do you see that 0? Tell me about this vector field. Incompressible. Why is it incompressible? Because the divergence is 0, but why in the application does that make sense? It's incompressible. There's no tendency of expansion or contraction in this field. Why not? Put a bunch of water in a box and try to make that box smaller. Good luck, right? So why is it incompressible? Because it's water, right? It's water. There's no, the molecules are getting further apart or closer together, right? It's water. It's water flowing. So that the kind of like the density is the same. So this makes sense. Okay, so now we got to do the divergence theorem. And what did we say that f dot ds was? It's going to be the sum of? Yeah, so like d, so I'll call it d for that, plus the hemisphere, h. What's the triple integral of the divergence? 0, because the divergence is 0. What was the surface integral of the flux of the disk? Negative pi. So 0 equals negative pi plus the one we were asked to do. Equals? What? Negative or positive? Positive. Why does that make sense as positive pi? I thought the water's flowing down. What's that? Right, now we're talking about the divergence of or the flux through a solid. So now this is outward orientation. So outward orientation would mean positive coming out downward out the hemisphere. Yeah?
So if you had different flow rate of the water in different places, that wouldn't be different divergence. That makes sense. If it was flowing water.
No, it could be different flow rate in different places. Right? Because that'd be like a river, right? Like some places the river is stagnant or moving slowly, other places it's running quickly.
The divergence is still 0.
Yeah, divergence will still be 0. I think.
Like it was flowing faster upward and to the right, and slower down to the left.
Mm-hmm.
And that's still.
That's a good question. Yeah, I'd have to think about that. Yeah, any comments? Any thoughts about that? What's that? Okay, yeah, so because it's a pointwise phenomenon, it would still be the divergence would still be 0 if it's changing speed. Yeah, let me think more about that. Okay, so we answered number 2. So the flow rate is through that whole hemisphere is pi, and the top disk's negative pi, but we know the water is going down through the top disk and then down out through the hemisphere also. Okay, now there's another function g. So g is up here. So g is this one. So for g, we want to find the circulation around the boundary here. So here, this is C, and this is and notice there's a 1/2 here. So this is the vector field G. So we want to find the circulation of G around C. So what symbol should I write for that? Mathematically, what am I asking you to find? What's that? Yeah, what is that? What kind of integral is that? Single, double, triple?
Simple.
And what do we call those in general? Line integrals, right? That's a line integral. Circulation, line integral of? Well, G now. So it'll be G dot dr. Quick, go. Is that how you parameterized it?
Yeah.
So what's G going to be? What's our denominator? 1 every time, right? 0, Z is 0, so our denominator is 1, so we get sine t.
It is like a normal way when you do cross products. Yeah. That's why it might make more sense to me.
What's this? Negative 1? One half, don't forget the 1/2. I keep telling you to not forget it. I forgot it. 0, 2. Is this how you set it up? Yes? No? What's that? Okay, so we'll talk about that in a second. So this is doing the line integral, the circulation integral directly, and what do you get? Interesting, negative pi. And what was that equal to? Negative pi was also equal to what? The flux through the disk. Observations. So negative pi was the flux through the disk. It was also the circulation of G around the boundary. So what might we say? What's that? F is the curl of G. Is F the curl of G? Why would it make sense? Yeah, because so if this surface integral, this flux integral is equal to the circulation around its boundary, then that certainly looks a whole lot like Stokes' theorem, where F is equals the curl of G. So could we verify that? Can you verify that? What would you do? Find the curl of G. And so rather than, I trust you can do that. It's just an algebra process. So I'll just tell you that yes, it is. F is the curl of G. Just because these are both equal to negative pi does not confirm that. But it raises a suspicion, right? And then if you were to find the curl of G, you would find that it is the original vector field that gave you F. Okay? So this kind of example kind of brings together divergence theorem and Stokes' theorem together. So because we could write what? So the line integral around C dot dr is the same as the flux of the curl of G around S, I think we call that D, right? We call that D. And that equals, what did that equal?
whole thing minus the.
Right, the divergence of E, the hemisphere, right? Of the divergence of what? The curl of G, right? The divergence of the curl of G, dV, minus the double integral of the hemisphere of curl of G would be this one. So I'm out of room. So curl of G is always the same as F, so I'll write F because I don't have room to write curl of G. But all those curls of G are F. So what? It brought together a line integral and flux integrals and a triple integral and brought together the divergence theorem and Stokes theorem. Follow all that? What is kind of? Where did I lose you? Right? So we started by doing this directly because we had F, right? We had the curl of G, we had F, so we did this directly. We found this using the divergence theorem indirectly, right? And then I introduced G, and we saw that just the line integral around G was the same as the surface integral of that disk. And that we suspected that was Stokes' theorem at work. Just in time. Okay, hope you enjoyed it. Study hard.